In this video, we're just going to talk a little bit more about Riemann sums and then start introducing the notation for an integral. First of all, we're going to find the area below x cubed plus 2 on the interval from 0 to 2 with 4 equal intervals. So, of course, from 0 to 2, the intervals, we go up by 0.5s. Okay? So you can see those are going to be kind of our breaking spots. So the first one, left-hand sum, means that from 0 to 0.5 for this first interval, the left side sets our height. From 0.5 to 1, the left side sets the height. From 1 to 1.5, from 1.5 to 2. So you'll notice that this is definitely, when we find this, going to be an underestimate. Anytime a function like x cubed plus 2, anytime a function is increasing and concave up, and make sure you see that it is increasing and concave up, anytime that happens, the left-hand sum will be an underestimate. So in each of these things, the width is 0.5, so I'm just going to put 0.5, 5, 0.5. And the heights I would get by evaluating the function. So I did that over here. Let me bring that in. So this first one is just 2. It's just looking at the value at 0. The value at 0.5 is 2.125. The value at 0.5 is, at 1 is 3, and at 1.5 is 5.375, like that. Okay. Now, you'll actually calculate those and then add those up, and that will give you the left-hand sum. I'm not going to do that just in the interest of time. I'm going to rely on the fact you can do that. Okay. Next, we're going to do the right-hand sum. Okay, so let me erase here if I can. And here, as we go from 0 to 0.5, 0.5 will set our height. Now you can see, my bad rectangles notwithstanding, you can see that the right-hand sum will definitely give us an overestimate, as it will for anything that is increasing and concave up. So we still have 0.5 this time. This height is 2.125. This one is 3. This one is 5.375. And this one is 10. And again, we multiply those together, get the 4 areas, then add them, and that would be our right-hand sum. Finally, the midpoint sum, we would let from 0 to 0.5, we would let 0.25 set our height. From 0.5 to 0.1, we'd let 0.75 set our height. Here we'd let 1.25 set our height. And here we would let 1.75 set our height. Now I think you can see this is the best estimate, and you don't really need to think about over or underestimate with midpoint. But let me bring on here the other value. So now you can see our widths are still 0.5, but here 2.016. I'm going to go 3 decimals. 2.422, 3.953, and 7.359. Okay, and that will give us our midpoint sum. The following represents a velocity graph for an ant walking trip in millimeters per second. How far has the ant walked in 4 seconds? Well, when we're talking about a distance and we're given velocity, we need to find the areas under our velocity graph. So how far has the ant walked in 4 seconds? We go to time 4, which is right here, and we count the area. 1, 2, 3, 4, 5, and then this would be 6. So the ant has walked 6 millimeters. Okay. So how far is the ant from his or her starting point? Well, 6 millimeters away. Okay. How far has the ant walked in 5 seconds? Well, now 5 seconds right here. So, we look at the area, and it's 7, the total area. So the ant has walked 7 millimeters, and it's 7 millimeters away from its starting point. Now, you'll notice from our work with velocity graphs a while back that at time 5, the ant changes direction. Positive velocity means forward motion, negative velocity means backward motion. So at time 5, the ant starts moving backwards. So the next question says, I'm going to leave that 7 there because it would just be easier to know that area. It says, how far has the ant walked in 6 seconds? Well, 6 is right here. Okay, and this little area right here is 1. So the ant has walked 8 millimeters. Okay, 7 millimeters forward, 1 millimeter backward, so the ant's walked 8 millimeters. But how far is the ant from the starting point? Well, the ant walked forward 7 and back 1, so the ant is at the 6 millimeter mark. Okay. Next, how far has the ant walked in 8 seconds? Well, 8 seconds is right here. Okay, this area is 5. So the ant has walked 7 forward, 5 backward for a total of 12 millimeters. And 7 forward, then 5 backward, it's 2 millimeters away from its starting point. Now, we talked a little bit on Friday, what can make our estimates even better? Well, the simple answer is more rectangles. Okay, if we're willing to do more rectangles, like in our opener today, I'm spelling this wrong. In our opener we did 4, but if we were willing to do more, we certainly would get a better estimate. So that's the simple answer. What can we do? Now I'm going to introduce some notation. You see this down here. This is what's called an integral. Okay, it looks kind of like a stretched out S. And let me just explain this. More rectangles, of course, the beauty is, what if we could have an infinite number of rectangles? So this represents this sum. Remember, we get the height of the rectangle by evaluating the function, and we get the width by saying how far the x is apart. So this is the height multiplied by the base. This is the area of a rectangle. And this represents, we're adding up all of the rectangles, and if there grew to be a limit, or rephrase that, if we kept adding the number of rectangles, it had a limit, of course, as n approached infinity, it would approach the true area represented by this, the integral from a to b of f of x dx. Now the integral, this comes out of your book. The integral is essentially a shorthand way of writing that we're finding the area. So for our opener today, where we were doing the area from 0 to 2, okay, those would be our bounds. Okay, so where we're finding the area from, the function, which is called the integrand, well, our function was x cubed plus 2, and then we put a dx here. The dx represents the variable of integration. For now, we're going to be pretty much only doing in terms of x, but that doesn't mean we have to. We certainly could do in terms of y as well. And another kind of thing I just want to point out, similar to our ant walking forward and backward, is area above the axis is considered positive, area below the axis is considered negative, meaning this adds to your total, this subtracts from our total. So this would represent that ant walking forward, this would represent the ant walking backward. Now it could be any rate, it doesn't have to be a velocity graph, it could be gallons per minute. This is the amount flowing in, this is the amount flowing out. So let's just do a couple quick examples with this notation and using some geometry. You can see here, hopefully you see this is the graph of the absolute value of x. We're finding the area from -1 to 2. So I'd write that as an integral from -1 to 2, the absolute value of x dx. The AP exam does not penalize you for forgetting the dx, but I would get in the habit of writing it. It often helps us to know how we get the bounds and what we're referring to. It's very helpful to remember that, and it seems notational now. It seems like you're just writing it, but it really will come in handy later. Well, let's just use some geometry. This, of course, is a triangle. Height of 1, base of 1, so 1/2. This is a triangle. Height of 2, base of 2, so 2. So the total area is 2.5. I like fractions, so I'd write this as 5/2. This is a semicircle. If you can recall from pre-calc, circles are x squared. The equation for a circle is x squared plus y squared is equal to the radius squared. The radius here is 2, so damn. So if you wanted to solve for y, do that, and then we'd have y equals the square root of 4 minus x squared. Now I'm going to put a little plus or minus here, because that's what, I mean, notationally that should be there. But I'm only talking about the top half of the circle, which means I'm only talking about the positive part. So I'm going to take that out, because the function we're looking at is just the positive square root of 4 minus x squared. Please note, square roots are not distributive. You cannot simplify this to be 2 and x. Okay, you can't distribute the square root over a subtraction, so this is as simple as it gets. Okay, so our function, square root of 4 minus x squared. We're finding the area from -2 to 2. Well, area of a semicircle, of course, is 1/2 pi r squared, because it's only half the circle. Here the radius is 2, so 1/2 pi multiplied by 4, 2 squared, would just be 2